Hi everybody, welcome to the Electron X channel. Right now, I would like to go into a little bit more of the details on calculating power in AC circuits. And as we know, AC circuits have three different types of power: real, reactive, and apparent power. And you can see my video intro to real, reactive, and apparent power to get more of the mathematical background of where those three powers come from. This video is going to be more about the calculations of those types of power, but let's do a quick recap of those three different types of power. To start off with, there is real power, and this is the type of power that gets consumed by the system. And what really happens is it gets converted into a non-recoverable form like heat, and it's associated with resistors, which convert electrical energy into heat energy. The second type of power is reactive power, and this is the type of power that cycles back and forth in the system between sources and devices, and specifically with inductors and capacitors. And it's power that is not consumed by the system, because it gets converted into magnetic energy in inductors and then converted back into electrical energy, or into the electric field in capacitors and then back into the electrical energy in the circuit. And the final type of power is apparent power, and this is a way of combining the real and the reactive power into one quantity. And it's not just an idle quantity, it's not just a way of combining these two powers, it's a way of indicating the level of current that a system can support, even when that current is not doing useful work. So real power is designated by the symbol P, reactive power is designated by the symbol Q. And this is a little known fact, but the term mind your P's and Q's, which is sort of a mind your manners or pay attention, was first used by Nikola Tesla when he was mentoring younger electrical engineers when he worked for Westinghouse Electric. Actually, that's not true at all. I have no idea where that term came from. I just thought that would be awesome if that was true. And finally, apparent power is designated by the symbol S. Now, the derivation of these three types of power come from the equation for changing power over time, which comes from multiplying the voltage signal by the current signal, where the voltage signal and the current signal are sinusoids with the same frequency, but they may have some phase shift in between the two. And so that phase shift is actually a determinant of how much real power there is, how much reactive power there is, and how much apparent power there is. But again, I'm not going to go into the mathematical derivation of this in this video. You can go back to my intro to real, reactive, and apparent power to find out more information about that. And that video does talk about the derivation, or how you would calculate S, P, and Q for a system, not when you're looking at the sinusoid, but when you're just talking about the averages. And the apparent power is equal to the RMS voltage times the RMS current. Real power is equal to the apparent power times a cosine of theta, where that theta is the phase shift between voltage and current. So it's that phase difference, the phase angle of the voltage minus the phase angle of the current. And finally, the reactive power is equal to the apparent power times the sine of that phase shift. If you are solely looking at the apparent power on a resistor, and you either know the current through the resistor or the voltage across that resistor, you can also calculate the real power for that resistor. So the power is equal to either the RMS voltage squared over the resistance, or the RMS current squared times the resistance. Similarly, for the reactive power, if you have either a capacitor or an inductor, and again you know the voltage across them or the current through them, you can figure out the apparent power. The apparent power is equal to that RMS voltage. I didn't designate RMS there, but that is RMS voltage squared over the reactance of that capacitor, or the voltage squared over the reactance of this inductor. And it's also equal to the current through that component, so the current through this capacitor here squared times the reactance of that capacitor. And if it's an inductor, it would be the current through the inductor squared times the reactance of that inductor. By convention, but also because of the phase shifts, reactive power for a capacitor is negative, and reactive power for an inductor is positive. And this comes from the power triangle, or the phase shifts between them. So if I have a real power and an apparent power, sorry, that should be a reactive power, I get this apparent power, and this phase shift is positive. This would occur for an inductive reactive power, whereas if I have a real power and a reactive power that's capacitive, that goes in the negative direction, and that's from a negative phase shift, or where the current is leading the voltage, like it does with a capacitor, and I get the apparent power there. All right, let's take all this background theory and apply it to a couple of examples. So I have an example here with a 100-volt source that's applied to a series combination of a 10 ohm resistor and a 10 ohm inductor. Let's make the assumption that that voltage is an RMS voltage. If it was an RMS voltage, if it was peak, then I would need to convert it to RMS to do all of my power calculations. So for this circuit, I want to calculate the real power that's used, the reactive power, and then finally the apparent power. So what I'm going to do for this particular circuit is start off, well actually I'm going to do the calculations in two different ways. I'm going to start off with calculating the total impedance of this circuit. Of course, the total impedance is the real component plus J times the reactive component. That's the value in rectangular coordinates. I can convert that into polar coordinates and I get 14.14 ohms with a phase angle of 45 degrees. Next, I can calculate the current. And once I have the current, that's going to be the current through the resistor and the inductor. Then I can use I squared R and I squared X for figuring out the individual powers for those components. Current is, of course, voltage over impedance. So I have 100 volts with a phase angle of 0 divided by 14.14 ohms with a phase angle of 45 degrees. And I get a current with a magnitude of 7.07 amps and a phase angle of negative 45 degrees. The power that gets used by the resistor, so that's the real power, is equal to the magnitude of I squared times R. So that is 7.07 amps squared times 10 ohms, which works out to 500 watts. And the apparent power used by the inductor, well, not really used, but absorbed and released by the inductor, is equal to the magnitude of I squared times the reactance of that inductor, which is again 7.07 amps squared times 10 ohms, which also works out to 500, but this is reactive power, so my units are VAR. According to the power triangle, the apparent power is equal to the vector sum of the real power and the reactive power. That gives me S. So the magnitude of S is equal to the square root of P squared plus Q squared. So in this case, that's going to be equal to the square root of 500 squared plus 500 squared, 500 watts plus 500 VAR, and that works out to 707 VA for the units of apparent power. I could have also calculated S in a different way if I go back just to where I've calculated the current there. S is also equal to the RMS voltage times the RMS current, which of course also works out to 707 VA. And I can let you confirm as an exercise that the real power used by the resistor is equal to S cos theta, where theta is this phase difference between voltage and current. So phase angle of voltage minus phase angle of current, so that theta would be 45 degrees, not negative 45 degrees. And you could also confirm that the reactive power is equal to that apparent power times the sine of theta. So as a reminder of what we have just calculated, we've calculated 500 watts, so the amount of power that gets used by the system on average. 500 VAR is this power that gets cycled back and forth between the inductor and the source. And this apparent power is a quantification of the RMS voltage times the RMS current, even if those two are out of phase with each other. So here's another example where I have two components in parallel with each other. And it's going to be the same type of analysis even though these devices are in parallel. I can calculate the total impedance, figure out the current, and based on that current, figure out S and then P and then Q. Or alternatively, I have 1,000 volts that's applied across each one of these elements. I can calculate the individual powers for these two elements. So that second method is actually going to be easier to do, but I'm going to go through the first method first. So start off with calculating the total impedance. The total impedance is equal to the impedance of the capacitor, the inverse of the impedance of the capacitor plus the inverse of the impedance of the impedance of the resistor, and then I take the inverse of that. So that's 1 over negative J5 plus 1 over 10 to the minus 1. Fairly simple, fairly straightforward to figure this out. It's just a little bit of complex arithmetic, and that works out to 4.46 ohms with a phase angle of negative 63.4 degrees. So from the total impedance, I can calculate the total current. Of course, that is voltage of 1,000 volts, phase angle 0 over 4.46 ohms, phase angle negative 63.4 degrees, which works out to 224 amps with a phase angle of 63.4 degrees. Now I can figure out S, which is going to be the RMS voltage, 1,000 volts times the RMS current, 224 amps, which is equal to 224 kVA. P is S cos theta. So 224 kVA times the cosine of negative 63.4 degrees, and that is 100.3 kVA. Similarly, Q is the apparent power sine theta. Plug numbers into that, and I get 200.3 kVA. Okay, I've got my powers calculated, but I'm going to confirm this with an alternative calculation. That's actually a little bit easier in this particular case because I've got these components in parallel. I know the voltage that's across them. So for the resistor, I can calculate the power as 1000 volts squared divided by the resistance of 10 ohms. That works out to 100 kVA. The reactive power, same voltage applied across the capacitor over the 5 ohm reactance of the capacitor, works out to 200 kVA. And then from the power triangle, I have my P and I have my Q, which is negative in the negative direction because it's capacitive, and I can figure out S from that. So S is equal to the square root of P squared plus Q squared, or 100 kVA squared plus 200 kVA. So 100 watts squared plus 200 kVAR, forgot the R there, kVAR squared. Plug those numbers into a calculator and I get 223.6 kVA. These numbers are off by a little tiny bit because I used some rounding in my calculations over here, but you can see that my real power is basically the same, my reactive powers are basically the same, and then my apparent power also basically the same. Okay, I'm going to leave it there for these introductory calculations for real, reactive, and apparent power. Don't forget to mind your P's and Q's. Thanks for watching. I'll see you in the next one. I don't know why I always say I'll see you in the next video. I'm not going to see you in the next video. You're not even going to see me in the next video. I'll probably keep saying it because it's habit after all of these videos that I've created, but know that I know that it's not true. Thanks for watching.